supposed to be, hard to tell what it's supposed to be. All right. And one of the many things that makes it confusing is the chapter numbers are wrong in the online book. And we want recognizing C code constructs, chapter 6. All right. That's the right one. Okay, good. All right. I should say a word about the projects first because you're going to do all this stuff, and I just put them up revised today. There are many versions of Microsoft Visual Studio, and they keep moving all the web pages and changing all the links and changing all the versions so that you just want to cry. So I went and found a really old version of stuff that will actually run on your Server 2008 machine, and I put it on my own server. So since that is Microsoft proprietary stuff, I can't just give it to the whole world, so I put it on this page here where you need a name and password to get in, which I'll write up here because people always forget it. Okay, so with that top secret information, all right, you can get to this glorious page, and in the 126 section, you can now download this thing, which is 1 gigabyte, and that is a version of Visual Express that will run on Server 2008. Of course, it's kind of amazing because all I really want is like GCC, but you have to get 1 gigabyte of stuff, and if you get later versions of Microsoft, it takes 5 gigabytes of stuff to give you GCC because, of course, they give you 100 more complicated things with it. Anyway, that you can install easily on VMware on your Server 2008 machine, and I imagine anything later too, but it's a good idea to just use it here. And then you can write your own code and you can compile it. So let's get rid of this junk. So I just start here and run Visual C++ 2008. This is their free edition, the Express edition of their C++ compiler, but the only thing we're going to do is C. C++ is a superset of C or something close to that. So if you make a file new project, and all this is in the instructions, of course, then you can make various kinds of projects, but the kind we're going to make is Win32 console applications, so you don't have any windows or anything. Just run in text, that's the easiest thing. So this is going to be demo. All right. And say OK. And next and finish. And it makes a very simple application. So this just has include, this is the equivalent of stdio.h in Linux, the standard libraries that you need. And this just returns 0 and does nothing else. Now it also includes printf, so you can actually make hello world. You can put in a printf line here. Gotta have it lowercase. Well, in Linux you have to have it lowercase, so I don't really know about Windows. I'm not gonna try it, printf.
It should still be case sensitive.
It's still case sensitive?
Right, so
Yeah, well that's reassuring. So you can put hello world here, semicolon. That should work. Let's see, let me bring up the project here because there might be some weird syntax issues. But the first thing is just to install this junk and make print hello world. And it is just that. Okay, fine, good. So once you got your code here, you build it with build solution. And then it has a window down here showing you the logs as it proceeds, and if it works, you get it succeeded. If you made some kind of typographical or format error, which of course is what everybody hates about C, because it's very, very picky, one missing semicolon and the whole thing is shot, you'll get errors here. Anyway, when it's working, you can now run it. I think it's debug, start without debugging, we'll just run it, and it just prints hello world, and then it automatically puts press any key to continue. Now, if you want to see the executable, it has put it in a sort of non-obvious place. If you go open Windows Explorer, which I can do here, go start in the Administrator Home folder. It is in Documents, Visual Studio 2008, Projects. Then you have a separate folder for each project, and then it goes in the Debug folder, is where the executables are. So there's the glorious demo.exe, which if you double-click it, should open in a terminal, and then again, maybe I'm going to have to run it in a command line. Yep, it's going to close if I do it that way. So I got to go there, Documents, Visual. Okay, and then Projects, and then Demo, and Debug, and then dir, I can now run demo.exe, and it prints hello world. Okay, so that's all I wanted to show you. That's the very simplest program you can make. Now, the other thing you can do with this, which is of course what's of interest to us, now that you can write simple programs in Windows, we want to see what they look like in assembler, because the malware we're going to look at, of course, is not going to be nice enough to give us C source code in most cases. So I want to run IDA Pro free, which is good enough for what we're doing here. Now I want to open that file. It's a PE executable, like every Windows executable, and I just have to find it. It's here in this whole mess, projects, demo, debug, demo.exe. Okay, now, remember IDA Pro has to actually do a lot of work to disassemble it, and even make some guesses to disassemble it, and I have to agree to all that. And when it's done, I get this nonsense here where I just see a start routine that doesn't go anywhere, which is normal. This is the way Windows works. It has like a startup bit of code and another startup bit of code, another startup bit of code, which is not the code that's interesting, and that can be kind of annoying. One simple way to get past this is to just start with a string. Like here's a string I recognize, hello world. So you run it to see what it does, find something it prints out, and then find the string it's going to print out, and then you know that's somewhere inside the interesting code. So if you double click that, you go to where the hello world variable is stored, which is in a data section, not a text section. But if you go to the right here, there's a thing called data xref, and that's going to show you, see now I found where the hello world string variable is stored, but I would like to know where the hello world string variable is used. And that's here in main plus 20. And if you hover over it, it'll show you a few assembly language instructions showing, of course, that it's going to push that onto the stack and then call print. This is part of the code that does the print. And if I want to go there, I just double click this. And now I'm in what I sort of wanted to see in the first place and expected to see, which is main. If they'd asked me, I would have just started IDA's display at the main, but they didn't ask me, and so anyways, make it hard to find. So this is wmain, which is equivalent to the usual main we see. This is where it all starts. This is where it does good things. And the simple thing you can see here, since this program does nothing except say hello world, the only thing you can see here is something that you should be familiar from the Linux work we've done. This is what a function call looks like. You call a function, and before that, you push something on the stack. And in this case, all you have to do is push a offset to the string onto the stack, and then call print. Because it only has one, this particular print statement just has one fixed variable, one fixed argument, which is a string. So all it did, these two assembly language instructions together are printf hello world. You put the hello world on the stack, and you call print. So that's the simplest program. So let's make a little bit more complicated one to have something to look at. Go back to here, and I'm going to just make a new project and call it demo 2. All right. And finish this nonsense. And here we are with another blank one. So now I'm going to up here put an integer I, and down here I'm going to have an integer j. Now, this one up top, let me get rid of this window at the bottom, it's not very interesting. All right, this one at the top is a global variable. Notice it is not inside any method. Like this is the tmain method, and this is outside all methods. You can put variables out there, and they'll be available to every part of the program, and shared by every part of the program. So if one part was to change this value, that would change it everywhere. Those are global variables. And it's actually, I think, considered a pretty sloppy programming practice to use them. I used to use it in the old days of Fortran. But anyway, that's what that is. That's a global variable. This is the more common local variable. That int j is defined inside main and only exists in main. If I go into some subroutine like printf, that variable is not there unless I passed it in as an argument, in which case there's a copy of it down there. So this is a local variable. That's a global variable. Let me just go to my project instructions and see how I did this there so I'm being consistent. This is now project 8, where you do a few very simple things in C. And so here, yeah, I signed it to 1 and 2. Let's just do that. Int I equals 1. You can put a value in the variable when you first define it, or you can, of course, do math on it later. Okay, so now let's make a more complicated print statement like printf hello numbers are %d and %d, and even a carriage or %d. the carriage return be all fancy and stuff, I, J, parentheses. There, that is, I think, more or less correct syntax for C. So this is going to print that line. It's going to put I in the first variable and J in the second variable. So now this printf statement now has three parameters, J, I, and a fixed constant format string. And I have two variables that are going to be stored in different parts of memory, the global variable and the local variable. Local variables are stored on the stack because they only exist while you're running that one routine. When you go to another routine, they're gone. Global variables are stored in one of those data sections. So let's watch this go. Compile this with build solution, and run it with debug, start without debugging. And there it is. Hello, numbers are 1 and, oops, ampersand D. I used an ampersand instead of a percent, so it didn't print the 2. So let me fix that. Let's close this. And yep, that's an percent, but that's an ampersand. It just treated it as a literal thing to print, which was okay. And then notice, this is why C is so different than other languages. I had an extra variable here, J, that was never printed, and it didn't complain about it. Other languages would complain or even fix it or something, but C will usually just keep going. Anyway, it won't try to second guess you. Anyway, so let's build solution. And in fact, if I looked at those messages, there might have been a warning telling me about that. But anyway, this time it succeeded and nothing failed. Debug, start without debugging. Okay, now, hello, numbers are 1 and 2. That's what I expected to see. So my program is now doing this in all its glory. So let's take a look at it in IDA. New, don't save database, something they're all upset about, because if I had paid money for the professional version of IDA, I could save comments and notes in here, and it would be a really bad idea to lose them. You can't do that in a free version anyway, so there's no point worrying about it. A PE executable, okay. I don't want to do this one. I want the demo 2, which is here. And a debug demo 2. Okay, then again, I tell IDA, just go ahead and figure out what's in there, making whatever guesses you have to do. Once again, it sends me to a stupid place. I go find a string. There's the string that I recognize, hello numbers. So I double click that. That gets me to the R data section where the string is stored. And here's where I get to the code. Main plus 32 is what's going to actually use it. So when I go there, I've now gotten the code that does this. So let's take a look at this one, and you'll see. Here I'm going to get ready to call printf. Now I'm going to push not just one variable, but 3 pushes here. So the first thing I do, the code that's used for this is actually from here on down. 1, 2, 3, 4, 5, 6 assembly language instructions now to call print. The first thing it does is move EBP plus var8 onto EAX. Now EBP is the base pointer to the base pointer of the stack. The stack goes from EBP to ESP. So EBP plus var8 is some distance down the stack. Now I could try to figure out what var8 is, but I don't really care. It's on the stack. This is a local variable. So it pushes that on. Then it's going to get another one and push EAX. And then it's going to call, that's what it loads something off the stack and pushes it. Then it gets something called I, which is IDA Pro helping. Remember, because in this case, it actually had source code. So it could get real meaningful variable names, which was I. This is the global variable, which I defined outside there. So it has the letter I, and so it's going to push that, and then it's going to push the format string, and then it's going to call printf. So you should understand that's how a function call looks in assembler. And this I is the luxury you won't usually have of actually an alphabetical variable name. Otherwise, it will have an automatic name generated by IDA Pro, which will be something like var underscore 004087, just some location where it's stored. All right. Anyway, that's the simplest case.
It's memory address, right? Not
Yeah, a memory address. Normally, it's just a var followed by memory address because IDA Pro doesn't know what to call it, so it just labels things by their memory address. This is what we get for having symbols available, which is that box that popped up. In this case, since I have the source code right in the same directory, it will link it in. Just like in some of your early Linux projects, you had the source code in the same directory, and you could actually put breaks in GDB from source code and not from assembly code. So, all right, so let's take a look here. And we've been through a few of these, so there's what a function call looks like. There's one calling just fixed values, 1, 2, and 3. And so we found the source code. By the way, there is a link 6a if you want to find out what all these goofy things are that happened before main in Windows. There's a bunch of preliminary function calls that just sort of get in the way. IDA Pro, but you can read about them there. So you go to strings and the xref to find the code with the string in it. And this is this one that pushed values of 3, 2, and 1, and then it pushed a format string, and then it calls printf. So that was, in this case, it was 5 lines of assembler to do one printf. By the way, also notice that they go on in reverse order, from right to left. So first 3, then 2, then 1, then the string. That's the way arguments are always pushed. Backwards, because it's the stack. When you pop them off, they'll come off in order. All right. So I mentioned the difference between global and local variables. All right. Local variables are on the stack. Global variables are somewhere else. All right. And so here's the one with the local and global variable. And here's the code that does that. So EBP is local on the stack. Global has, in fact, an alphabetical name here like I. But if it was without source code, it would just be var underscore address. All right. So I got a few iClickers about that stuff. Grab one if you need one. That's good. Yes. Okay, there we go. Actually, I can get rid of this thing. All right. So, which opcode places X where printf can find it? All right. Guess I'll wait till 40 on this one. Although I'm thinking 10 may be all there are. All right. So that's push. When you call printf, the arguments have to be pushed on the stack. You can, by the way, do it with move. Sometimes you'll see that. Move to EBP plus 8 or something, which is another way to put things on the stack, but usually you use push. All right. Good. How about this one? What opcode will move EIP to the printf entry point? I'll quit at 30. All right. So when you call printf, one thing it has to do is move into printf, and that's what call does. Call is the assembly language command to jump to some routine somewhere else, and it's followed by the address of printf. Or really, it's called by the global offset table entry, which is then pointed to another layer of indirection, which then goes to printf. But anyway, that's what actually moves the EIP to stop counting sequentially through your instructions here and go someplace else. All right. Where is X likely to be? Quit at 30. All right. It's going to be stored in one of the data sections, so A is a logical place. That's where a global, not X is a local variable, pardon me. So it's stored in B. Now, I'm seeing a lot of disturbing answers here. You can't store any variables in a register. Registers have data flying in and out of them with every instruction. You store something in the register, it's not going to be there for long. If you want something to persist for even a few lines of assembler, you've got to store it somewhere else. It's got to be either on the stack, which is going to have an address like this, EBP plus something, or somewhere in a data section is logically where you store things. These are the only, EAX is used for temporary values during a calculation, and EIP is the instruction pointer, and that's what our sloppy overflows have been doing, is putting junk in EIP, and that just causes the machine to crash, because EIP has to stay in the valid code sections, like the text section. If it wanders out of there, the thing will just crash. So these two are somewhat reasonable answers. Those are disturbing answers. Anyway,
I thought you had just said that the global ones are the ones that would say like bar 8.
no, the global ones are in a different section. This is an address in a data section intended for global variables that are intended to stay the same, called the program execution. This is the stack. That's what locations on the stack look like. And so they exist only during the operation of one subroutine. All right, and these are the ones you overflow in stack overflows. All right. So anyway, let's carry on. All right, where would you likely find B? I used to worry about this.
You gave the answer in 10 seconds.
I used to worry about that. And at least half the time it makes no difference at all. Which is, these iClickers are quite helpful for a teacher because it is very frequently the case that absolutely nothing I say is penetrating. And this is the way at least you know about it. I'm not sure I can help though, but do what you can. But there is another way to use them, which might be appropriate in this case, where the students then break into groups and argue with each other to see if they want to change their answer. They do that in physics. Anyway, let's see if this is getting any better. Well, that's good. All right. So anyway, there's really only two choices. Global variables are stored someplace like that, and local variables are stored someplace like that. But I ought to mention, the other technique of doing this is you put up a puzzle, the students vote, then you don't tell them what the right answer is, then groups of 3 have 1 minute to talk about it, then they get to vote again. And usually 1 out of 3 has an argument for the right answer. Anyway, that's another way to use these things. Haven't done it, maybe I should. Anyway, so which value is pushed on the stack first? I'll quit at 30. All right, and B goes on there first. They go on in backwards order. Good, a popular answer. Okay, good. So, let's talk about the next thing here, arithmetic. Very simple. So we're going to take some variables. They're all local variables. Then add and do a division. You can also do multiply and subtract. In these modern processors, when I was a lad and I learned assembly, there was no multiply and no divide. You kids have it easy. So here's the assembly language code produced by that. It's going to take 10 called 0AH and put it in this location on the stack, put 2 in that location, then put something in EAX, and then add 2 to it this way. And then it's going to take something else and do an IDiv to divide something. And when you divide it, it's sort of like calling a subroutine. Division requires you to have things that are quad instead of double size and have them in certain registers. So it's always EAX divided by something, and the answer goes in, I think, EDX at EAX. It's a little bit complicated. So all these 4 statements are needed to implement a division, which really is sort of like a function call and uses the registers in a special way. This is the problem, because if you multiply or divide, the answer does not necessarily have the same number of places. So you have to have extra room available, so it uses 2 registers. Anyway, I wouldn't worry about it. It's not that important for us unless you're going to do scientific floating point calculations. So here's some examples. That will put, this puts 10 in there, so this puts 2 into a local variable. That puts I, by the way, into EAX, I being a local variable. and on you go. A little bit of detail there about the double and quad, but I don't really want to push it at this point. Division is kind of nuts to do at the assembly language level anyway. Now branching if is probably more important. So I'm going to have int I equals 3, then if I equals 3, print something else, So that is the kind of code that you want to be able to recognize. And so here's what it's going to look like. Of course, in IDA, it's going to show something up there and then a jump not 0. So one way it will go here if it's not 0, and here if it is 0. And so this way, you can see it's going to call printing this message, I is 3, and here it's going to print that message, I is not 3. So it's really pretty easy to spot ifs in the graph view in IDA Pro. That's why you'll have these 2 arrows coming out, one red and one green. So this is the easiest place to look to recognize that kind of code. All right. Now for loops are a little more complicated. And by the way, they're designed in such a way that they very often get off by 1. But anyway, this is how you write a for loop. For I equals 0, I less than 100, I plus plus. So it will start I at 0. It will then do whatever's inside here, which is a print. Then it will increment I with the I plus plus. And as long as I is less than 100, it'll do it again. That's what it works. So there are really 4 steps here. Initialization, starting I at 0. A comparison to see if it's less than 100. It executes the stuff inside, which is just printf. And then it increments or decrements with I plus plus or I plus minus. You could, by the way, put I plus equals 10 or something, but very few people do that. Unless you have a special case, you just go up by 1s. So you can look at those 4 components, and you'll find all 4 of them in your assembly. So this is the initialization. It takes the 0 and puts it on that variable. Where's that variable stored? At the first line there? What's that first line? Where does that 0 go?
The local variable.
Yep, a local variable on the stack. EBP plus something. Then it's going to jump. Now this is, by the way, quite common. What might seem like a logical flow to you doesn't seem logical to the compiler. So now it's going to jump down to here, skipping over that stuff. So let's look at what it skipped over. What it skipped over just takes something from the stack and puts it at EAX, adds 1 to it, and then puts it back. That's increment. Now there is an assembly language command called increment, but the compiler chose not to use it in its wisdom. Who knows? That's increment by 1. It doesn't increment by 1 before doing the loop. It does the loop and then increments by 1. This is how the compiler chose to implement that for some reason while they're putting the code here and then jumping over it. You'll often see this sort of thing. So this is going to put that number on the stack. What is that number? That's 100, right? 6 times 16 plus 4. That's the 100. So then it's going to compare. It's not going to put it. It's going to compare this value to 100. Is it equal to 100 or not? And if it is greater than or equal to, then it's going to jump off the bottom here because it's done. The loop is over. If it's not greater than or equal to 100, it's going to do this stuff. And this stuff is going to put something in ECX, push it, put some offset to some string in here, and then call. So it has 2 pushes. This is the print that has 2 arguments. And it prints I equals D, and then the second argument is the value to print, which was put in ECX and then pushed on the stack. So these 4 statements here are the printf. And then down here it's going to add something to the ESP and jump back to run to the top, way up here, and repeat the loop again. And notice that IDA Pro, in order to help you, has actually named some of these places. Location 40100D, location 401. These are flags, named locations, and so it jumps to that one, D. And that one there jumps to this one. It's trying to help you. This is why this is pretty hard to read. Like, why even bother giving it a stupid name like that? The reason is because you might figure out what it means, and then you'll change this name in IDA Pro, and the name will percolate everywhere else. And that's why you want to save your database, because you could be changing these names to meaningful names and understanding the malware. And this might take days and weeks. So you'll want to keep saving your work. But in the free version, we don't get to do that. All right. So then there are arrays. Array is another data structure you're commonly going to use. C++ has the ability to define complicated data structures like you did in the heap overflow project where you would have a string followed by a pointer. But we're just going to do a simple one here, just an array of integers. So we make a local thing called bracket 5, that is room for 5 integers. Then we fill it up. Make a loop for I equals 0, I less than 5. Set a of I equals I and b of I equals I. And there's another b up there, which is a global variable. So I have a local variable and a global array, both being filled by a loop. So I just want to see how that looks in assembler. And it looks like this. You're going to have a loop. So again, you've got a local variable made and loaded with 0. That is the counter. Then you have, again, it jumps over things because I'm using the same compiler that likes to do things that way. In there is just an increment. Loads something to EAX, adds 1, and then puts it back. And what's down here is now going to be the comparison where I compare it to 5. Remember, it was for I equals 0 to 5. So if we're done, we jump off the end of this. If we're not done, we're going to do this stuff. This is going to assign a variable in the element in the array B. Now B is stored in var 14, and A is stored in this D word 4A4000 because A was a global variable, so it's far away. B is here in this var 14, which is on the stack. So this is the kind of math you're going to see. This is the way you usually spot arrays. There'll be a loop, and then there will be this nonsense where you have some kind of base address plus a counter times 4, because there's 4 bytes in an integer, 32-bit processor, 32-bit word. So you have to jump through the memory locations 4 bytes at a time. So ECX is something being incremented here, and I'm multiplying it by 4 and adding it to some kind of base. And the EBP puts it on the stack. So this is the local address of one element of that array. And there's a whole series of 32-bit words, one after the other, stored on the stack, which is what you saw in the projects when you put in something like 100 A's and you look at the stack. You see all these A's in a row there. And here is the one that loads the global variable, so it's this D word 40,000, starting with that as the base, and then moving from that ECX times 4. And if you look at how the C code was written, there was this I, and you use I here, and you use I here again. So that's why you see the I is apparently stored in ECX. This must be I, this var 18 thing. And then you use ECX times 4 to say how far into this array you are, and ECX times 4 to see how far in that array you are. So that's a clue. If you were storing complicated data structures that were bigger than 4 bytes, this would be some number other than 4. But you'd be jumping forward in fixed units of data. Anyway, that's the idea, and I think that's the most complicated one I wanted to show you. There's a couple more examples in the chapter, but these are the main data structures I want you to be able to spot. And the more you do this, the better you get at it, of course. At first it seems very difficult, but you get used to it. Like I mentioned before, if you're a beginner and you can't figure this stuff out, just look for the things on the right you can read, like printf and push and gets. That'll give you some orientation as to where you are. All right. So you can find the code. The simplest way is look at strings and use xref to find where a string you could see was used. That'll get you into the part of the code that's interesting. Function calls, you put the arguments on the stack in reverse order, and then you use call. For variables, you got global and local. Global is in memory and available to all functions, and local is on the stack and only available to one function. Yeah?
For the global variables.
Yeah, you can define a global.
It does go in the stack when it goes through the loop.
What's that?
The global
Yeah.
variables.
What about it?
Do they go on the stack when?
No, it doesn't go on the stack. Unless you were to
refer to the memory?
Yes, you refer to a memory location. It's like those strings. It's stored in a memory location and you refer to it by address. So any function can refer to it. It's often in a different segment. That's the idea. So they're not that commonly used. It's considered a somewhat sloppy thing to use, although it's going to come up next week in the form of mutex, a similar concept. If you have two functions and they need to talk to each other, that is one way to do it. What's more common is to pass a value to it if you want to tell this function what that function is doing, or to pass a pointer to it if you want that function to change something back here. But a global variable is another option, and I think it's an old-fashioned way to program. I used to do it well back in the days of Fortran 4 in like the 80s, but anyway.
It's also really common in like real-time control systems, like car operating systems, but like that's not malware.
Yeah, that's right. But I mean, that's why there are cases when you use it, but it's like go-to. It's considered sloppy style. You're supposed to have everything in little modular components that can be moved around and tested independently. but this is sometimes the best solution for a certain small job. Yeah. All right, then there's arithmetic, which means you put stuff in registers, then you add or subtract or divide the registers, and then you put it back in the variables. That's typically the process. You notice that's pretty much how you do everything. In this code, it's even incrementing things that way. Take it from memory, put it in a register, add one of the registers, then put it back in memory. That's why I say storing something in the register is for the birds, because the registers are just constantly being used, data flying in and out of them. All right, so I got a few eye clickers about that stuff, and I think that's it. All right. So, which line is most likely to require JZ? And you have 5 lettered lines there. Good, I think there's one right answer to this. I vaguely recall last time I taught this course, some student found errors in my slides, so we'll see. Hopefully I fixed them all. The most common kind of error is that there is a second right answer I didn't notice. Quit at 40. All right. That's E. E has this if, do something, and that's what you normally use a JZ for, or perhaps a JNZ, or a JGE, or anything. There are many different ways to do it. But JZ will jump if something is 0. So that is one way you can implement that if statement. All right. Which line declares a local variable? Ah, good. All right, I'll quit at 30. All right, and that's these local variables here inside main, so B is the only lettered line that has that property. Good, okay. All right. Which line requires IDiv? Good, looks like I can quit at 25. All right, IDiv is integer division, and that's what line D does. Good, all right. All right, which one requires call? I'll quit at 25 then. All right, and that's of course E, which has that call to printf. Whoa, all over the place. Not good. A call is what calls a subroutine. None of this calls a subroutine except that line right there, printf. Call jumps into some routine where it's going to do something and then come back. This just defines a variable, and a lot of people are hitting C. Both of these just defines a variable, that does addition. Neither of them require calling another routine. This is the only one that calls some other routine. All right. How about this one? Which one requires push? All right, I'm quitting at 25. All right, let's see. Well, again, not very popular answer. The way a call of a subroutine happens is you push the parameters on a stack and then you call. So this is going to take 2 lines of machine code. It's going to push an address to this string and then call printf. Printf is going to look on the stack for the parameters. So you typically see push, as many pushes as there are arguments, and then a call. And all those things are included in this one printf statement. Anything that calls a subroutine. All right, one more of these. Which line declares a global variable? right, I guess I can quit at 20. All right, and that's, of course, the first line, A. That's the global variable. Good, all right. Well, you guys have got your global and local variables, and the rest of this, I hope will become more clear when you do the projects where you practice a little more of this. If you don't get too much of it, don't give up. It's okay if you start with only a weak grasp of assembler. As you continue, you sort of dig it deeper gradually. At first, it seems very alien, so don't give up easily. Anyway, let me stop the recording, and I'll see who won. And then I will go to the lab and help anybody that wants to work on their projects today. This is 126, chapter 5, I think. Hard for me to tell. 6, okay, good.